Hello, this is MEI Further Maths Core Pure. We're in the third complex numbers section and on the first video on converting Cartesian to modulus argument form. For this video you will need to understand radian measure, which is not included in AS Maths, so you may not have met this yet. There's a video that you can watch to learn about radian measure. And while you're there, you may want to look at the addition formulae for trigonometry, which you will need for the third video in this series. We're going to start by defining the two terms modulus and argument. The modulus of a complex number is simply the distance of that number from the origin O. We usually say mod z. And we can calculate mod z using Pythagoras. We just use this triangle here to find that length r. The base of the triangle is x and the height is y, so the distance r is the square root of x squared plus y squared. The modulus is always a positive distance, and note that we're just finding the distance, so we don't need to put an I in here with the y. It's just y squared. Pause the video for a moment while you work out the modulus of these complex numbers. OK, the point 1.5 is on the real axis here, and its distance from the origin is simply 1.5 units, so its modulus is 1.5. For the point 3 plus 2i, we need to look at this triangle here with base 3 and height 2. So the modulus of this complex number is 3 squared plus 2 squared, all square rooted, which is root of 9 plus 4, or root 13. The point minus 4i is here, and that's just 4 units away from the origin. But note that if we do use the formula 0 squared plus 4 squared, we do get that answer 4. And finally, for the point minus 4 minus 4i, this length here, we look at this triangle with height 4 and base 4, and that's 4 squared plus 4 squared, all square rooted, which is root 32, or 4 root 2. Notice that strictly speaking, we should put in minus 4 and minus 4, but we're squaring both, so it doesn't actually make any difference. Certainly you don't want to put those minuses outside of the squares, or you'll get a very strange answer. The argument of a complex number is the angle you turn through to get from the positive real axis to the line joining the number to the origin. We calculate this number using basic trigonometry, so that in this triangle here, the opposite side is y and the adjacent side is x, so that tan theta is y over x. Theta is then the inverse tan of y over x. We measure the argument in radians, and we choose values between minus pi and pi for the principal argument. Sometimes your calculator will give you an answer that's not in that range, so you may need to add or subtract pi to get the principal argument. Pause the video for a moment while you work out the principal argument for these numbers. OK, the number 2i is here, and you can see clearly that that is 90 degrees or pi over 2 radians round from the positive real axis. So the argument of 2i is pi over 2. For the number 3 plus 4i, the angle that we want is this angle here. So we use this triangle with height 4 and base 3, so that tan of theta is 4/3, and the argument is therefore inverse tan of 4/3. Making sure that your calculator is in radians mode, you should get an answer of 0.927 radians. For the complex number 3 minus 4i down here, you can see that the angle theta that we require is simply the negative of the answer to the previous one. So the argument of 3 minus 4i is just minus 0.27 radians. For the complex number minus 3 minus 4i over here, you can see that this angle here is theta as we measured it before, but the angle that we want is this angle here. This angle is pi minus 0.927 radians, which is 2.214 radians. But of course this is going clockwise, and so we need that to be negative, minus 2.214 radians. We've been using the Cartesian form of complex numbers, but sometimes writing it in modulus argument form can be more useful, and we'll see this in some of the following videos. To convert from Cartesian to modulus argument form, first calculate the modulus using Pythagoras. Remember that the modulus will always be positive. And then calculate the argument using basic trigonometry. You can put any negative values of x and y into this formula and then decide whether or not to add or subtract pi. Or you can simply draw a quick sketch and use basic GCSE trigonometry, which might be a safer way of doing it. Having found r and theta, we can write z in this form. We know that x is equal to r cos theta and y is equal to r sin theta. So we can write z is r cos theta plus I r sin theta. Or we can take out the factor of r and write it z equals r brackets cos theta plus I sin theta. And this is what is usually meant by writing a number in modulus argument form, or sometimes polar form. Pause the video for a moment while you try this question for yourself. OK, the first step is always to draw a sketch, and I've marked on the length r and the angle theta that we need to find. For r, we simply use that right angled triangle and note that r squared is root 3 squared plus 1 squared, which is 4, and therefore r is the square root of 4, which is 2, always taking the positive value. We want the angle theta, but we're going to use the right angled triangle to find that angle alpha first. We can see that tan alpha is equal to root 3 over 1, and therefore alpha is inverse tan root 3 over 1, which is pi over 3. And therefore theta is equal to pi minus pi over 3, which is 2 pi over 3. Our complex number z is therefore 2 brackets cos 2 pi over 3 plus I sine 2 pi over 3. There are more notes on integral on converting from Cartesian to modulus argument form. That's the end of this short video. The next video in this series is on converting modulus argument form to Cartesian form.